So the transistor switch seems like a kind of a superfluous circuit, and we don't really actually we're not really testing it and showing what it's good for. And you'll have to just take my word for it that you can have a tiny signal control a huge signal. I mean, this is the basic premise of a transistor anyway, right? That's the premise of amplification. In this case, we're not using it as a proportional valve though, meaning like if I wiggle it a little bit, I get bigger wiggles, but the wiggles move together, right? In this case, we're just putting some DC voltage and slash current into this thing. It goes into full conduction, and the current is limited by the. It's one of the questions in there that you're investigating in this section, that you could calculate a current, but the actual current going through it is the voltage across the light bulb, and whatever the load is what dictates the current. And the thing is now, if when you wire light bulbs together, I don't know if you realize this, but everything in your house is wired in parallel. So that every time you turn on a light bulb or a motor or something, the amount of current going in through your meter out on the outside of your home is going faster and faster. And it just has to be, number one, if a light bulb burns out, you don't want the whole house to not work anymore, right? There's Christmas lights that used to be like that. And number two is that this way, when you turn things off and on, they run at their design spec. Because if you had light bulbs in series, they would get dimmer each time because the current would go down. So you want to always supply everybody with their voltage, but that also means that you have to be able to supply varying amounts of current. And this is why sometimes power failures aren't that common anymore. But in fact, a funny story is I was visiting CERN, where the LHC collider is, and everybody lives across the border in France because it's so much cheaper than Switzerland. But in France, they have many nuclear reactors, so they heat their houses with electricity, which is usually not a very efficient way to do things. But that's another point. The fun part about this is that every fall and every fall they have all these power failures because everybody starts turning their heat on all at once, and the system isn't ready for that surge in current. Because what you have to, if you think about it for a minute, the way a generator works, and I suppose I'll set it up there. It spins at a constant speed because they don't regulate voltage. Remember, I described how power is delivered to your house, where the return is the earth itself. They only run one wire, actually. They run more than one, but any given place that they send electricity is just one wire, and the return is through the earth itself. So the voltage that you measure is going to be a function of the resistance of the earth and the distance from the transformer, because there's going to be a voltage drop. And this is why AC beats DC, because in DC you can't have the generator more than a kilometer away, whereas in AC you what they do is at just before it goes to your house. I'm sorry. Oh boy, I think yeah they're trying anyway. Good they're not in there. Thank you. Um, they what happens is the last step before it's sent towards your house is it's at 5,000 volts, and you can have it. Your house can be 2 miles away. That's what they use as a rule of thumb. So even if it goes down to 3,000 volts, by the time it makes it to your house, there's a transformer on the telephone pole right outside your house that steps it down to your 110. And even then, you're not guaranteed. They don't guarantee the amount of voltage. They guarantee the frequency, though. They're very, very careful to maintain the frequency. And that has to do with how fast the generator is spinning. So when there's a demand, for, how do they satisfy the demand for more current? In principle, you could spin it faster, but then you would be changing the voltage and the frequency. I should demonstrate that to you guys. So it's a good thing I brought the whole mess up here after all. Anyways, what they do is that in my generator, there's one coil spinning. In a real one, they have many, many coils spinning, and then they just, when they need more current, they just put in more. You'll see on the right side. I'll table this for a moment, but they engage more coils, and that's because you need varying amounts of current. All right, so there's my. I'm in a big digressive mood today, huh? More than normal. I was espousing quantum mechanics, elementary particle physics. I was on a roll before most of you got here. Where the hell was I? I know I'm on the planet Earth. I'll remember. Yeah, no, I'm joking. The transistor switch. What's neat about it is that you can switch a tiny switch can switch a big load. And most importantly, instead of a push button, you could have a very fragile printed transistor that can switch a big load, and that's the big thing here. And this is why years ago switches and dimmers. Oh, look at that! They found that little fragment of used to be massive. I remember in my church, they would dim the lights sometimes, and there was this rheostat that was the size of a pizza. This is an example of what that looked like inside. It's a heavy ceramic and this resistive wire, and they had I swear to God, it was this, and they had a big handle on it, and one of the I don't know what they call them, deacons or something like that, would dim the lights down. But now when you look in that place, it's gone, and there's this tiny little box, and what's in it is a derivative of this circuit. Now, the last thing you do, the middle part is with the saturation curves. That's too incomprehensible. So part of what I got going on up here, it's got a power supply, and I want. And here's another thing. See, you guys should either come over or just stand up and take a look here. Now, I can control the voltage, and I can see these things now set, they're slaved together. Yeah, come on up here. Let's just come up here. I wanted you to observe the behavior of this thing. So it has a certain resistance, and if I change the voltage, it changes the current, huh? So what's happening here, they're in parallel, so I get the sum of these two currents. Now, in a battery, because of the internal resistance, slowly but surely, as I increased the amount of current flow, the voltage would go down, right? And remember, and this is really a direct short, almost. And we know by math we should set the voltage to 0. But a power supply is different. What a power supply does, I can increase the voltage, but then all of a sudden, the current won't go up anymore. It's reached and notice the voltage is not going up anymore either. And that's analogous to the battery behavior, but not exactly the same. And one thing now, I've got 10 amps running for this. I have to remember not to leave this on too long because I could cook on it. It's not quite so warm just yet. But notice what happens when I open this thing. You see that? When I close it, there's no spark. But when I open it, and that's because it's an inductor, and inductors are flywheels. And this is not that heavy duty of a coil. Across the way, we got these two massive coils, and when I do this with that, it goes for like 2 or 3 seconds. It just keeps arcing across. And that can be dangerous. At the very least, what it does is it would wear switches out. And so back in the day, the original house switches, they were actually rotary, and inside, you'd crank it, a spring would wind up, and then it would rotate this thing, and it was basically, these things were sticking down, and the thing would rotate into it. And they had to be massive you demounce it to preserve the contacts, number one. Number two, you get to the point where there's so much stored energy that it becomes dangerous. Remember, too, to make an arc, you need 3 times 10 to the 6 volts per meter. 3 million volts per meter. So that's a pretty hefty voltage that all of a sudden is built up, and it's all because of the stored energy. So you're going to hook up those batteries, and when you open the switch, you're going to see a huge spike on your oscilloscope. And we use the battery because if we use the regular function generator, we might burn something out. So remember, battery. So okay, so let's see if I can. Oh, let's go back to what go back to our seats because it'll take me a little while. And notice it's so much current. The fan is on to cool it off, right? Yeah, I'll hook up an oscilloscope here and I'll actually go over the operation of. It's actually called an alternator, not a generator. Okay. So you play with this thing a little bit. There's not a huge amount to be learned other than when you do the calculations, you notice that you're actually not supplying much of a signal at the base, but you're able to deliver quite a wonk of current to make that light bulb, relatively high amount of current to make that light bulb go on. Okay. And then that's called a power transistor. And you notice it's very massive and it has that tab coming out of it. And that tab would be connected to what's called a heat sink. There's a couple of them inside your, oh, here's stuff, the printout that I needed. I thought I left at home. Killing trees. Well, I'll see. I'll find somewhere around here. These metal things with fins on them to dissipate the heat. And if you were to open up your power breadboard, you'd see a power transistor like that. And they're specifically made. In fact, I think that has to do with the emitter-based collector. One of those 3 is attached to that metal tab, actually, on certain of these transistors. And that's I don't know why electrically it's done, but physically it's done to dissipate heat. And so it doesn't break when it gets hot. And what's this one? Oh yeah, so this is where you use a battery and then add the diode. Okay, so I wanted to go over this example. And so you're told that you want to make an emitter follower. You're only allowed to use a single voltage. And you want to drive a 4.7K load. If you set up the blocking capacitor properly, then that isn't a part of the load. Notice that the output impedance of the source is 10K. So you can't just simply put a voltage divider here, right? Because that's 1/2 when in fact you need at least 100K there. Or you'd have to lower your output impedance of your source to 400 ohms. So that again is why we use an impedance follower, because it changes the apparent impedances. So you should already have this in your logbook. So in principle, we're just going to flesh out your details in your logbook. It's fine to go back and don't worry about the business of back annotations. So similar to a homework problem, we can't attenuate by more than 10%. And the book shows 15, we have 12 volts. And we want a quiescent current. So when it's not doing anything, we only want 0.5 milliamps. By the way, this quiescent current is a limitation on computer CPUs. What happens in the computer CPU is the quiescent current comes about because of quantum tunneling across they're not NPN transistors. But if just imagine now, I've got these 3 slabs of semiconductor, and if I want to make things smaller, you imagine that the base is smaller and smaller and smaller. And at some point, the conduction electrons start tunneling across the base, and that becomes an output signal, even if the transistor is doing nothing. And in computers, that's exactly what's going on. As they make the transistors smaller and smaller, there's more and more leakage current, and if nothing else, they produce heat. If you know anything about badass gaming computers, they come with these active refrigeration. Actually, if you've seen the inside of these things. So, anyways, we need to design this thing. So we have our 12-volt load, and we want to center the output. So and he says, let's be lazy, and even though we know there's going to be a voltage drop across the base, we're just going to say that we're going to center the output at, in this case, 6 volts. And so if we want a 0.5 milliamp quiescent current, then we need the voltage drop across RE to equal 6 volts. So I equals V over R, and we know what is V, and we know what is I, so 6 volts over 1 times 10 to the minus 3, and we come up with a value for that resistor. So that's fairly easy. So in the case, and the next step would be to center our biasing network. And as I mentioned before, he chooses to ignore the voltage drop across the base because one could say, oh, I need to make this 6.6, say, right? He just says, make R1 equal to R2. Let's see if my other one has the notes. So you're going to have to bear with me a little because instead of getting this ready before class, I was yapping. Here we go. So we want to center this thing. I wrote that already. And so just so there's it's very straightforward. In this case, it's 6 volts from here to here. But I know it's 6 volts across the emitter because I want it to be halfway, right? I mean, if I wanted the voltage somewhere else, then I don't just simply plug in that voltage. It's the voltage drop across the emitter resistor. So if I wanted the voltage at that point to be 4 volts, then I would have, oh, give me a minute. If I want the voltage there to be 4, oh, it is the same. Never mind, I'm wrong. Duh. It's that simple, the lower resistance of the voltage divider, right? So it's the voltage across RE. If I wanted it to be 4 volts there, I put 4 in the equation. All right, good, sorry. All right, so what's next? The biasing resistors. So, okay, let's first just make them equal. I said that already. And what is then the R Thevenin of those two things? And we know in general that the R base, the input impedance at the base, is going to be beta times RE. So we need to have our biasing network to be able to feed into that without compromising it. Now the subtlety here is that in principle we've seen effects of the load resistor, but because we're talking about the DC bias, the load resistor doesn't matter, so we don't have to care. So in their case, he had chosen 15K, and I don't remember, let's see what ours would be. it's going to be 6K, 7.5, no, 0.5 milliamps. I put 1 here. So that means 12K. So RE equals to 12K. And then times 100 becomes 1.2 megohms. So that means that we need, on our Thevenin of our bias network, equal to 10 times, right? So that is equal to 0.12 megohms, or 120K. So if the two of them are equal, that means we need two 240K resistors for the bias network. We did not have to consider the load resistor because we're going to put the blocking capacitor there. And we also noticed that we haven't even come close to worrying about the 10K output impedance. Everything is much higher than that. I mean, we're pushing it at 120K, so we're right at the level. But we're going to even look at it some more. Okay. So, what's next? So now we talk about what, for the blocking capacitor, what value do we choose for the blocking capacitor? So we have to decide is, what is that R prime there? So the Zn is the R Thevenin of the base, R Thevenin of the bias, and then R in at the base. But now we can't, because it's signal, we can no longer ignore the loading resistor. And did we say exactly? I can't even remember what if we. Yeah, it's a 4.7K. So we have to do the parallel of 12K and 4.7K. And I'll leave that to you guys. And that allows us to figure out what is the blocking capacitor. Now we've already done something similar to this. And then here it is with all his values that he calculated for his particular setup. Yours will be similar. So your job is to make sure you have down, you've already taken notes on that. I've gone through it with you now. I want you to build this thing today, and I want you to do our standard procedure to figure out, measure the Zn of this thing, and verify that it matches what your calculations say it's supposed to be. And then show me the output on your oscilloscope. Because it seems like most of you are about to do you're either doing the transistor switch or you're about to, right? So our project today is to design and build this emitter follower. I'm a little weirded out that he has, well, we're gonna do it again in chapter 5, but we're gonna have a chip in front of us with the transistors hidden inside. And I think it's important that you guys go through this procedure of calculating this and building it and looking at the output and saying, wow, here's what I designed it to do, and it's doing it, right? Up to this point, you've just made up circuits that you were shown, right? So wire it up, show me that it does what it's supposed to do, and measure the Z in. That one's the easy one. It's harder to measure Z out, so I just want you to measure Z in and compare it to what you calculated it was going to be. Okay? Very good. So I'm going to stop there, and then I'll get that demonstration wired up, because it is pretty... You guys, yeah, none of you have taken Physics 2200 in person, I think, huh? And in fact, most of the I don't like disparaging my colleagues, but I can show you calculus with my oscilloscope inside there. All right, time to stop the recording, especially